Whether you're a tech enthusiast, industry professional, or just curious about the future of AI Agents Unleashed will keep you informed and inspired. Buckle up and get ready to unleash the potential of AI.
Welcome back, everybody. Ready for another deep dive. This one I think is really, really fascinating. We're going to be talking about multi-agent reinforcement learning, MARL.
Yes, MARL. It's kind of like, imagine you take all the smarts of AI and you're not just doing it with one, you're doing it with many, many AIs. It's like an orchestra, but with a lot of high tech.
Yeah, that's a good point. And, I always like to kind of set the stage for what we're looking at. So, for this deep dive, our source material is we're going to be looking at excerpts from this recent survey on MARL. And, we want to really uncover how these AI agents, how they learn to cooperate, what are the hurdles that they face. And then, the cool part is what are all the crazy possibilities they unlock?
We'll even get into, the idea of AI simulating entire societies. I mean, this could totally revolutionize, how we think about urban planning, how we think about how economies work. I mean, so many different possibilities.
It's pretty wild when you start to think about it, right? I mean, imagine if you had self-driving cars that could negotiate traffic like, I don't know, like a perfectly choreographed dance. You have these robots in a warehouse that are working together seamlessly. I mean, that's what we're talking about with MARL.
Yeah, but before we get to those sort of like super inspiring applications, I think it's probably helpful to kind of like break down the basics.
Okay, let's do it. What are we talking about when we talk about like the fundamental building blocks of MARL? What are those?
So at its core, it's all about these agents interacting within an environment, right? So they've got actions they can take. And the goal is they need to learn which of those actions will lead to the best outcomes. You can kind of think of it, it's like, when you're training a dog. But instead of giving them a treat, they get something called a reward for making good decisions.
Oh, interesting. Okay. So the agent is like the dog. The environment is like your house.
Yeah.
And then the actions are kind of like sit, stay, fetch, that kind of thing.
Yeah. And those rewards, those are like those yummy treats, right? That you use to kind of motivate your furry little friend. But this is what makes it really, really interesting with MARL. We're not talking about just one dog learning tricks, right? We're talking about a whole pack of dogs learning and adapting at the same time.
So then that kind of brings us to this key difference in MARL, right? You need those agents. They need to learn not just on their own, but they need to learn how to cooperate effectively.
Yeah, precisely. And this all happens within what's called a stochastic game framework.
Okay, stochastic game framework.
Yeah.
That sounds complex. Can you maybe break that down a little bit?
Sure. So stochastic basically just means there's randomness, there's uncertainty built into the environment. Think of it like those dogs that we were just talking about. But now they're playing in a park where squirrels might randomly, dart out, or other dogs might come by and want to play.
Right. So the environment is not static. You don't always know what's going to happen next.
Exactly. Yeah, it's dynamic. And what's interesting is that the actions of like one agent, those can directly impact the environment for all the other agents. It's kind of like a constantly changing dance floor. Everyone's trying to learn the steps and coordinate with their partners all at the same time.
I mean, no wonder this is considered a challenging field, right?
Oh, yeah.
So how do researchers even start to deal with this level of complexity? Is there like a method to the madness here?
Yeah, well, that's where, game theory comes in, right? Which is basically like a branch of mathematics that can help us understand decision making, especially in those situations where you have multiple players. So, you got to be strategic.
So you're bringing in the heavy-duty math to help these AI agents kind of play nice with each other.
Exactly. And one of the key concepts in game theory is this idea of a Nash equilibrium.
A Nash equilibrium. I'm not familiar with that one. What is that about?
So it's basically like finding that sweet spot, right? Yeah. Where no single agent can improve their outcome by just changing their own strategy, assuming everybody else keeps doing what they're doing. So it's a state of balance, I guess you could say.
Right. Okay, so can you give me like a real-world example?
Yeah.
Because I think that might help to kind of wrap my head around this.
Sure. Imagine you've got like a group of friends and they're trying to decide where to eat, right? Everybody has their own preferences, but they all want to end up at a place where, everyone's reasonably happy. And so that compromise where nobody feels like, oh, I could have gotten a better meal by going somewhere else, that's That's kind of like a Nash equilibrium.
Okay, okay. But finding that equilibrium, like in a complex game, like we're talking about with self-driving cars with, I don't know, hundreds of cars interacting, that's got to be a little bit more challenging.
Yeah, that's a massive computational challenge. Imagine trying to find that perfect restaurant spot, but instead of just a few friends, now you've got hundreds of friends. And they all have different dietary restrictions, they've got budgets, they like different cuisines.
Yeah, it's a lot to juggle. No wonder this is considered one of the most challenging frontiers in AI.
It really is. But the potential payoff is just enormous, which is why researchers are so passionate about it.
It's like, it's not just teaching one AI to be smart. It's like teaching a whole team of AIs to be smart and work together. That's the key.
Yeah. It's like taking, a bunch of brilliant solo musicians and turning them into a world-class symphony orchestra.
Oh, that's a beautiful analogy. But I imagine there are some unique challenges, right? I mean, what are some of the hurdles that researchers are facing when they're trying to get these AI agents to actually play nice together?
Well, one of the trickiest ones is something called non-stationarity.
Non-stationarity. I'm already intimidated. What does that even mean in the world of MARL?
So basically, it means that the environment is always changing as the agents are learning and adapting. Remember those dogs playing in the park, right? With those unpredictable squirrels.
Yeah, that ever-changing landscape.
Exactly. Now, imagine trying to learn a game where the rules change every time your opponent makes a move.
Oh, gosh.
That's basically what these agents are dealing with because each agent is learning, right, and adapting. Their actions are actually changing the environment for everybody else. So it's like this constantly moving target.
Oof, that sounds frustrating. Even for AI, that sounds frustrating.
It is. It makes it really, really hard to find stable solutions. They might think they figured something out, the best strategy, and then all of a sudden, whoop, the environment shifts and they got to start all over again.
So how do researchers even begin to address this? Are there strategies to help these AI agents, kind of cope with this constantly changing environment?
Yeah, so a couple of approaches that people are trying. One is, developing algorithms that are designed specifically to handle non-stationarity. And another one is to focus on creating agents that are more adaptable so that they can kind of, adjust to changes really quickly.
So it's kind of like teaching them to be flexible and think on their feet, so to speak.
Exactly. But, non-stationarity, it's not the only hurdle.
Okay, so what else? What else makes this field so challenging?
Another major challenge is something called coordination. So, even if all of the agents are super smart, getting them to work together effectively, it's surprisingly difficult.
Why is that? I mean, if they're all working towards the same goal, wouldn't you kind of naturally assume that there would be cooperation?
You'd think so, right? But in the smallest miscommunications or misunderstandings, those can snowball into these major problems. It's kind of like if you have a team of dancers and one person is slightly offbeat, it throws the whole performance off.
Right. The timing is everything, isn't it?
It is. So even if each agent is individually brilliant, they have to be able to communicate, coordinate their actions effectively. So the whole team can achieve that best outcome.
Precisely. And this is where things get really interesting because researchers are exploring all these different approaches to try to improve communication and coordination.
So what are some of those approaches? Can you give us a little preview?
Yeah. So one of the most exciting things is this idea of using graph neural networks. So, GNNs.
Okay, I've heard of, neural networks, but what makes GNNs so special for MARL?
Well, they're kind of is specifically designed to handle relationships between things. Remember how we were talking about the agents, how they're interacting in this really complex web of connections?
Right, like that dance floor that we were imagining before.
Exactly. So GNNs, they're really good at modeling those relationships. So it makes them perfect for representing the communication channels between the agents. So it's kind of like giving each AI agent its own little social network where they can all chat and share information with each other.
Yeah, that's a great way to think about it. And through those networks, they can exchange, different types of information, like what they're currently observing, what their goals are, what their intentions are, and even their strategies.
So they're not just blindly following instructions. They're actually having these conversations, strategizing as a team.
Yeah, exactly. Yeah. And that communication, it allows them to achieve these much higher levels of coordination and ultimately to be able to solve problems that are much more complex.
That is incredible. But with all this, I'm kind of curious, how do you even, like, how do you measure the success of these AI teams, with all this communication and coordination going on? How do you even know if they're doing a good job?
Yeah, that's a great question. It's actually one of the other challenges, like evaluating the performance of these multi-agent systems, because it's not as easy as, just looking at the individual performance of each agent.
Oh, okay. Why not?
Because their actions are so intertwined, the success of one agent often depends on what the others are doing. It's like trying to judge the performance of just one musician in an orchestra, right? You got to consider how they're all playing together to create that overall sound.
Right, right. So it's not just about individual brilliance, but about how those individual contributions are all coming together to create that, that successful performance.
Exactly. Yeah. And that's what makes it tricky because researchers are still developing effective ways to measure that collective performance.
Okay. So we talked about the challenges of non-stationarity, we talked about coordination, and even how to measure the success of these AI teams. But despite all of these hurdles, I can't help but feel this sense of awe at the potential of this.
Yeah, and you should. It's truly mind-boggling.
Let's shift gears for a second. I want to talk about some of the exciting possibilities, right? What are some of the really cool things that MARL is making possible?
So one of the, I'd say one of the most captivating prospects is the ability to simulate these incredibly complex systems. So, imagine entire economies or ecosystems.
Whoa. So we're not just talking about agents playing games or controlling robots. We're talking about AI simulating millions of individuals and businesses and even countries.
Exactly. Think about it like creating a virtual world where AI agents represent, different actors in an economic system. We could use that to study things like how different policies might impact the economy, how markets would react to changes in supply and demand, maybe even design economic systems that are more sustainable and equitable.
It's like a giant economic sandbox, right? Where you
Yeah.
can experiment with all these different ideas without having any real world consequences.
Precisely. And it's not just economics, right? I mean, we could use MARL to, simulate traffic patterns in cities or the spread of diseases or the impact of climate change on different ecosystems.
That's incredible. It's like having a crystal ball but powered by AI.
It is. And another really exciting area is teaching AI agents to communicate and cooperate effectively.
Wait, didn't we already talk about that a little bit?
Well, we touched on it, but there's so much more to it. We're not just talking about simple information exchange. We're talking about agents, developing their own ways to communicate, negotiating, forming alliances, even coming up with strategies together.
So we're talking about AI that can actually have meaningful conversations, make compromises, work as a team, just like humans do.
Exactly. Yeah. And that opens up this whole other world of possibilities for these AI systems.
This is mind-blowing. I mean, this is huge. I'm starting to get a sense of how transformative this technology could really be.
Yeah. And we're just scratching the surface. Another really exciting area is this idea of social learning, where AI agents can actually learn from each other, so it speeds up the learning process and it can lead to some really surprising and innovative strategies.
I love this idea, right, that AI agents can teach each other. But are there any downsides to this? Are there any risks with this kind of social learning that researchers are, worried about?
Yeah, that's a great question. And that's definitely something researchers are looking into. One concern is that, bias could potentially spread through the system, right? So if one agent picks up a biased strategy, it could quickly be adopted by all the others, and that could lead to some unintended consequences.
Right. So it's kind of like making sure that those social learning mechanisms are designed in a way that promotes, fairness and prevents the spread of harmful bias.
Exactly. And researchers are working on developing techniques to address this.
Yeah.
Incorporating diversity into the population of agents and encouraging them to explore a wider range of strategies.
So it's not just, an echo chamber of the same ideas.
Exactly. We want AI that is, intelligent but also fair, right?
Yes, absolutely.
Yeah.
Well, we've covered so much ground.
A lot.
We've talked about the fundamental concepts of MRL, the challenges, the opportunities, even some of the ethical considerations, which are really important.
Yeah, and I think it's it's important to remember that we've really only just begun to scratch the surface of this field. I mean, it's vast, it's fascinating. There's just so much more to explore. Everything from the specific techniques that researchers are using to train these AI agents to work together to the broader implications of this technology for society as a whole.
I know. It's so exciting. I mean, we've gone deep into this world where, AI agents they're learning to work together. They're solving complex problems, even simulating entire societies. It's just the beginning.
Yeah, I mean, as MRL research keeps advancing, I mean, we can just expect, more and more breakthroughs and applications that are going to completely transform the world as we know it.
Yeah. It's been such an incredible start to our deep dive into MRL, and I'm really excited. I think in the next part we're going to dive into the technical details a little bit more, talk about the specific techniques and algorithms that make all of this possible.
Yeah, I'm excited for that too. So, stay tuned, everybody. We're going to be back soon with part 2 of this deep dive. We're going to get even deeper into the technical details, kind of pull back the curtain a little bit on how these AI teams actually work.
So yeah, stay with us.
We'll be right back.
We'll be back.
Welcome back to our deep dive into multi-agent reinforcement learning.
Yeah, I'm ready to get into the nitty-gritty, you
Yeah.
know. We've talked about the big picture, the challenges, the possibilities. Now let's actually explore the techniques. How do researchers train these collaborative AI agents? How does that even work?
Right. So let's start with a concept called centralized training.
Centralized training. So is there some kind of master AI that's controlling everything?
That's actually a pretty good way to think about it. So in centralized training, you have this kind of mastermind AI that has access to all the information, all the actions of all the individual agents. It's kind of like, having a conductor leading an orchestra.
Oh, I like that. So this mastermind can see the big picture and guide the individual agents to play their parts in harmony, so to speak.
Exactly. Yeah, it can provide more targeted feedback and help those agents learn to cooperate better.
But wait, isn't the whole point of MRL to have those agents be decentralized, making their own decisions? If they're relying on a central controller, I mean, how are they ever going to be able to function on their own out there in the real world?
Yeah, that's a great question. And that's where the idea of decentralized execution comes in. So we might train them centrally, but the goal is for them to eventually operate independently using, all that knowledge and those skills they learned during the training process.
Right. So it's we're giving them the tools, we're giving them the training they need to succeed, and then we're setting them free to, tackle those real world challenges on their own.
Exactly. Yeah. It's kind of like like scaffolding, right? Once the structure is strong enough, you can take the scaffolding away.
Ah, that's a good analogy. I like that. So are there any other training schemes that researchers are kind of looking at in MRL?
Yeah, there's another one that's pretty interesting called off-policy learning.
Okay, I'm intrigued. Off-policy learning, what's that all about?
You can think of it as learning from the experiences of others. So in off-policy learning, agents, they can actually learn from the actions and the outcomes of other agents, even if those actions were taken, using completely different strategies.
So it's kind of like they're watching game replays.
Yeah.
Learning from the successes and failures of others.
Yeah, exactly. And that can really speed up the learning process and make it more robust to changes in the environment.
It's like they're tapping into this collective intelligence. They're learning from the combined experiences of the whole team.
Precisely. Yeah, and this brings us to another important concept, multi-agent credit assignment.
Multi-agent credit assignment. Oh, wow. Okay, that sounds like a mouthful. What's that all about?
Well, remember how we were talking about that challenge of evaluating the performance of these AI teams, how tricky it is? Well,
Yeah.
multi-agent credit assignment, it's all about figuring out which agents should get the credit for the team's success, or which ones are maybe to blame if things go wrong.
Ah, so it's who gets the MVP award?
Exactly. Yeah, and it's super important to make sure that each agent is getting the right feedback so that they can learn to improve their individual contributions to the team.
But how do you even begin to do that? How do you tease apart the contributions of these individual agents in a system where, everything is so intertwined?
It's definitely a tough problem. But, researchers are coming up with some pretty clever techniques. One way is to use something called difference rewards. So you compare the performance of the team with and without a particular agent's contributions.
Oh, interesting. So it's you're running a simulation, but you're like removing one player from the team and seeing how that affects the outcome.
Exactly. Yeah, it helps to isolate the impact of each agent's actions. And then there's another approach called value factorization. And that's where you basically try to decompose the team's overall reward into, separate rewards for each agent.
So it's like breaking down a complex equation into its simpler components.
Yeah, that's a really good analogy. And that can help us understand how each agent's actions are contributing to the team's overall success.
This whole idea of like multi-agent credit assignment, it kind of reminds me of something we were talking about earlier, which is communication.
Absolutely. Communication is essential, right, for any kind of successful teamwork, whether it's humans or AI agents.
Yeah, and we talked about those GNNs, those graph neural networks, as a way for agents to like communicate with each other. But are there any other approaches that researchers are exploring?
Yeah, so one really cool approach is called emergent communication. And this is where instead of programming the agents with a specific communication protocol, we basically just let them develop their own forms of communication through the learning process.
Wow. So it's like throwing them in a room together and see if they can figure out how to talk to each other?
Kind of, yeah. It's a fascinating area of research, and we're starting to see some really interesting results.
Yeah, like what kind of communication systems are these AI agents coming up with?
Well, in some cases, they develop really simple signals or symbols just to convey basic information. But in other cases, they've actually developed more complex languages with grammars and syntax that allow them to express a much wider range of ideas and intentions.
No way. So they're like literally inventing their own languages.
It's pretty amazing. And that ability to communicate, it's a key factor in their ability to cooperate and solve those really tough problems.
Okay, so we've got centralized training, we've got off-policy learning, we've got multi-agent credit assignment and communication. Are there any other techniques that researchers are using to train these collaborative AI agents?
Yeah, one that's becoming pretty popular is this idea of modeling other agents.
Modeling other agents. What does that mean?
So basically it means that each agent is trying to build a mental model of their teammates or even, their opponents to try to better understand their behavior and predict what they're going to do next.
So they're trying to get inside each other's heads.
Exactly. Yeah. And that can be a really powerful tool for improving, how they cooperate and how they coordinate their actions.
So how do they actually go about building these models?
So there's a few ways to do it. One is to use something called discriminative learning. And that's where the agents, they learn to classify or predict the actions of the other agents based on, what they observe, how they've behaved in the past.
So they're kind of like AI psychologists, right? They're analyzing the behavior of their peers and trying to figure out what makes them tick.
Yeah, that's a great way to put it. And that ability to model other agents, that's really crucial for creating AI systems that can actually function in those complex social environments that we find in the real world.
This is fascinating. It's amazing how researchers are taking inspiration from, human learning and social interactions to create these more intelligent and collaborative AI systems.
Yeah, totally. And another technique that actually takes inspiration from nature is something called stigmergy.
Stigmergy. Okay, I've never heard of that one. What is that?
So stigmergy, it's basically a form of indirect communication where agents are influencing each other through the actions they take on the environment rather than directly communicating with each other.
Okay, I'm not sure I follow. Can you give me an example?
Yeah, sure. Imagine, a colony of ants that are foraging for food.
Okay.
Right? They don't have a central command telling them where to go. They rely on this thing called stigmergy. So as those ants are finding food, they leave these pheromone trails behind, which the other ants can then follow.
Ah, so it's like leaving breadcrumbs for each other.
Yeah, exactly. And that simple mechanism that allows them to kind of explore the environment collectively and find those food sources much more efficiently.
It's amazing how nature just comes up with these really elegant solutions to complex problems.
It really is. And researchers are now, exploring how to apply those stigmergy principles to AI, specifically in the area of MRL.
Okay, how would that actually work?
So imagine you have a team of robots working together in a warehouse. They could use stigmergy to coordinate their movements so that they don't bump into each other and they can transport goods more efficiently. Maybe one robot could leave behind a virtual marker to say, like, hey, I'm working in this area, so that other robots know to avoid that space.
So it's like creating those virtual pheromone trails for the robots to follow.
Exactly. Yeah, and that could make those multi-robot systems much safer and much more efficient.
I love that. I mean, it's amazing how these seemingly simple ideas from nature can be like so powerful when you apply them to artificial intelligence.
It really is. And stigmergy is just one example of how, researchers are drawing inspiration from the natural world to create these more intelligent and adaptable AI systems.
Okay, so stigmergy is like a form of indirect communication. What other like interesting concepts are researchers exploring in MRL?
One that's getting a lot of attention is this idea of emergence.
Emergence. Okay, that sounds like something straight out of like a sci-fi movie. What is that all about?
So emergence, it refers to this phenomenon where you get these like complex behaviors that arise from the interactions of, simple agents that are just following simple rules.
So like the whole is greater than the sum of its parts.
Exactly. Yeah. And researchers are really interested in how to leverage emergence principles in MARL, to create these AI systems that can display those complex adaptable behaviors, even if the individual agents themselves are actually pretty simple.
Okay, can you give me an example?
Yeah, sure. So imagine you have a swarm of drones and they're working together to, search for a lost hiker in a forest. Each drone might have just a very simple set of rules, like, avoid collisions, stay within communication range, explore new areas. But from the interactions of those simple rules, you can get this really complex emergent search pattern
Right.
that allows the swarm to cover a much larger area and find that hiker much more effectively than any single drone ever could.
So it's like you're creating this like hive mind of drones that can adapt and solve problems as a collective.
Yeah, that's a really good way to think about it. And that kind of emergent intelligence, it really has the potential to revolutionize the way that we design and deploy, AI systems in the future.
Okay, emergence. That's a fascinating concept.
Yeah.
What other techniques are being used to like train these collaborative AI agents?
One that's really cool is evolutionary algorithms.
Evolutionary algorithms.
Well-
Okay, that sounds familiar. Didn't we talk about those when we were doing that deep dive on genetic algorithms?
You're right. Yeah, evolutionary algorithms are inspired by by the process of natural selection.
Survival of the fittest for AI.
Exactly. So researchers are using these algorithms to like evolve the policies of the AI agents. Imagine you've got like a population of agents that all have different strategies.
Right.
The most successful ones, they're the ones that get selected to like reproduce
Ah, interesting.
and create a new generation that has even better strategies. So over time, that population, it becomes more and more adept at solving the task at hand.
So over time, you get this population of AI agents that's just like getting smarter and smarter and better at working together.
Exactly. Yeah. And evolutionary algorithms, they offer a really powerful way to train these multi-agent systems.
This is amazing. It's like we're creating our own like AI ecosystem where these agents they're competing, they're cooperating, and it's driving innovation and like pushing the boundaries of what's possible.
That's a great analogy. And speaking of, pushing boundaries, another area that researchers are looking into is multi-level learning.
Multi-level learning. Okay, that sounds complex. What is that all about?
So in multi-level learning, you're training those AI agents to like operate at different levels of abstraction. Think of it like a hierarchy.
Okay.
Where you've got some agents that are focused on those low-level tasks like, maybe controlling the movements of a robot.
Right.
And you've got other agents that are more focused on like, the higher level stuff like planning and decision making.
It's like having a chain of command within the AI system.
Yeah, that's a good way to think about it. And that hierarchical approach, it allows you to create AI systems that are more flexible, more adaptable, and better able to handle those really complex tasks.
It's fascinating how like researchers are taking inspiration from human organizational structures and applying those to AI.
Totally. And just like humans, sometimes AI needs to, draw on past experiences, and that's where transfer learning comes in.
Transfer learning. I think I've heard that term before. What is that exactly?
So transfer learning, it's basically about reusing knowledge that was gained from one task to improve performance on a different but related
So
tasks.
it's like we're giving these AI agents a head start,
Yeah.
right? By letting them like build on their previous experiences.
Exactly. Yeah, it's a really powerful technique that can like really reduce the amount of time and data that you need to train these AI agents, especially for those complex tasks.
This is amazing. But with all this, I have to ask, are there any techniques that are like focused on the AI's ability to actually learn how to learn itself?
You read my mind. That's one of the most fascinating areas of research. It's called meta learning.
Meta learning. Okay, that's like we're going like deep down the AI rabbit hole now.
We are. So meta learning, it's all about teaching AI agents how to learn. So instead of teaching them to solve specific tasks, we're actually teaching them how to adapt to new tasks quickly and efficiently.
Wow. So it's like we're giving them the ability to become like self-taught learners.
Exactly.
Yeah.
Yeah. And that has the potential to really like revolutionize the way that we train AI systems,
Yeah.
make them far more versatile and adaptable than anything we've seen before.
It's incredible how like researchers are just pushing the boundaries of AI learning. What other exciting things are they working on?
So one that's getting a lot of attention lately is reinforcement learning with human feedback. So RLHF.
More LHF. Okay. What's that all about?
So it's basically about incorporating, human feedback into that reinforcement learning process. It's like having a human teacher, right? Who's guiding the AI agents, giving them feedback, helping them learn those right behaviors.
So we're kind of like bringing the human element back into the loop here.
Exactly. Yeah. And that can be really helpful, especially in situations where, like, it's hard to define those really precise reward functions. Or, if we want to make sure that those AI agents are behaving in a way that aligns with our values, human values.
This all kind of makes me think about like, the big picture. We've talked about a lot of technical stuff, but where does MARL fit into like the grand scheme of things?
That's a great question. And it brings us to like why Marowell is so important. We're not just trying to build AI that's smarter. We're trying to build AI that can actually work with us, alongside us, augmenting our abilities, helping us solve those really complex problems that we're facing as a society.
So it's not like AI versus humans. It's AI and humans working together as a team.
Exactly. And Marowell is really like at the forefront of that whole exciting, new era of collaborative intelligence.
This has been such an insightful journey. I mean, we've covered so much, the challenges, the opportunities, the techniques, even those broader implications of marijuana.
Yeah. But I don't think our exploration is quite over yet. There's one more really fascinating aspect of MRL that we need to discuss, and that's the concept of awareness levels.
Awareness levels. Okay, this sounds intriguing. I'm definitely ready to dive into that. What are we talking about here?
So think of it as like a spectrum of how much the agents, actually understand about their fellow agents in the system.
So we're talking about like how much these AI agents understand about each other's roles and their goals and even like their intentions.
Yeah, exactly. At the most basic level, you have what are called independent learners. And these agents, they're basically like lone wolves, right?
Yeah.
They're just focused on maximizing their own rewards. They don't really care about their teammates.
So it's kind of like everyone's trying to be the star player, even if it means that the team loses.
Yeah, exactly. And that can, obviously lead to like conflicts, and it can be really inefficient, especially in tasks where you need a lot of coordination. It's like having a basketball team where everybody's just trying to score and nobody's passing the ball.
Right. Okay, so if that's on one end of the spectrum, what's on the other end?
So on the other end of the spectrum, you have what are called tracking agents. And these guys are hyper-focused on adapting to whatever their teammates are doing, even if it means, sacrificing their own stability.
So they're constantly trying to adjust their behavior based on like what everyone else is doing, even if it means that they like never really develop their own like consistent strategy.
Yeah, exactly. It's like imagine trying to dance with a partner who just keeps changing their steps all the time, without any warning. You might be able to follow along for a little while, but you're never going to really get into a groove.
Yeah, that sounds pretty chaotic. So is there like a happy medium somewhere between these two extremes?
There is. That's where modeling agents come in. And these agents, they try to really understand their teammates by building models of their behavior. So they're predicting their actions and then adjusting their own strategies accordingly.
So they're kind of like they're always trying to anticipate what their teammates are going to do next and then plan their own moves based on that.
Exactly. Yeah, it's a much more like strategic and nuanced approach where you're balancing, your own individual learning with like a deeper understanding of the team dynamics.
This whole idea of awareness levels, it's really fascinating. Just it highlights how complex it is to design these like truly collaborative AI systems.
Yeah, it really does. And deciding which awareness level to use, it really depends on the task and how much coordination you need. For some tasks, independent learners might be fine. But for others, you really need those modeling agents, with those sophisticated modeling abilities.
It sounds like researchers really have to think about the big picture, right? It's not just how individual agents learn, but how all of those individual learning processes come together to achieve that collective goal.
Yeah, you got it. And that actually brings us back to a challenge that we talked about before, which is, multi-agent credit assignment. Remember, it's
Right.
all about figuring out who gets the credit and who gets the blame.
Right, because in a lot of real world scenarios, you can't really give each agent its own individual reward.
Right.
Right? It's like, in a soccer match, you get one final score for the whole team, not individual scores for each player.
Exactly. So research had to come up with some clever ways to figure out, which agents are contributing the most to the team's performance and which ones maybe are not pulling their weight.
Yeah. So what are some of those techniques again, just to remind us?
Right. So one approach is to use what's called difference rewards. And that's where you basically compare the team's performance with and without a particular agent. It's like, running a simulation where you bench one player and see how that affects the outcome of the game.
So you're isolating the impact of that one player's actions on the overall
Yeah,
score.
exactly. Yeah. And then another technique is called value factorization. And that's where you try to kind of break down that global reward into these separate rewards for each agent based on their unique contributions.
Yeah.
It's a complicated process, but it's really important for making sure that every agent is getting the right feedback so that they can learn and improve their individual game.
This all kind of ties back to that idea that we're not just training individual AI agents, we're training, teams of AI agents to work together effectively.
Exactly. And as we, create these more and more sophisticated MARL systems, it's really crucial to give them those tools and those algorithms that they need to communicate and collaborate effectively.
And speaking of communication, I'm still just like blown away by this idea that AI agents are like developing their own languages to talk to each other. How are researchers making that happen?
It's definitely one of the most exciting areas of MARL research. And, as we mentioned before, those graph neural networks, those GNNs, they're really playing a key role in that.
Those specialized neural networks that are so good at handling relationships.
Exactly. So by using GNNs, we can basically create those communication channels between the agents so they can share information about, what they're seeing, what their goals are, and even like their strategies.
So it's not just, blindly following instructions. They're actually like having these conversations, like discussing the best way to approach the problem and coordinating their actions as a team.
Yeah, and that communication ability, that's really what allows these AI teams to achieve those much higher levels of coordination and solve those complex problems that would be like impossible for a single agent to solve on its own.
This is incredible. But, I'm thinking in the real world, these AI teams are going to encounter situations where they have to like work with partners they've never met before.
Right.
So how do they handle those like ad hoc situations?
Yeah, that's a great point. It's kind of like being thrown into like, a group project with a bunch of strangers, right? You got to figure out like who's good at what and adapt really quickly. So researchers are exploring a few different ways to help those AI agents do that.
Yeah, like what?
So one promising approach is called population-based training. And this is where you basically train the agents on a bunch of different partners, each with their own, unique style, their own strategies.
Right.
And that helps them develop those more adaptable and robust behaviors that can then transfer over to those new situations.
It's like giving them a crash course in teamwork.
Oh,
Right.
yeah.
Exactly. Yeah. And then another technique is called off-belief learning. And this is where the agents are trained to be like less reliant on those assumptions about, how their partners are going to behave. They kind of learn to like expect the unexpected.
Right.
And that makes them much more flexible in those ad hoc team settings.
This just highlights how much like thought and ingenuity goes into, designing these truly collaborative AI systems. It's like this this blend of computer science and game theory and even psychology.
Yeah, it really is. And as we kind of wrap up this deep dive into MRL, it's important to remember that we're really just at the beginning of this incredible journey.
It's true. It's so exciting to think about all the possibilities. Right? We've seen how MRL can create AI systems that can solve these super complex problems, simulate entire societies, communicate, cooperate, adapt to new situations. I mean, it's really incredible.
And as this technology keeps evolving, I mean, we can expect even more breakthroughs, more applications that are going to transform our world in ways that we can't even imagine right now.
Well, to all of our listeners out there, thank you so much for joining us on this exploration into the world of multi-agent reinforcement learning. We hope you've learned a lot and that you're just as excited about the future of this field as we are.
Remember, everyone, the future of AI is collaborative.
And on that note, keep exploring, keep learning, and stay curious.